Okay.
Thank you.
Yeah, thank you, Anban. So we are now entering the second round of talks today, and there's 3 of them left. The first one is going to be by Jameson Rollins from LIGO, and he's going to talk about streaming data for the International Gravitational-Wave Detector Network. So whenever you're ready, Jameson.
Great, thank you. Well, thank you for having me. Can people see my talk and hear me okay?
Yes.
Okay, great. So yeah, my name is Jameson Rollins. I am the control and data systems lead here at the LIGO project at Caltech. And I want to talk about our the project that we're pursuing right now to improve our stream processing infrastructure. So, you know, like I said, we're improving the data processing, data distribution, stream processing infrastructure that's sort of long been in need of a refresh. And this reflects the continued priority of the field to enable more transient event discovery. I'll talk more about this. This new effort actually starts just downstream of our first storage. So it's I'm a little bit violating the principle of the workshop here. But in the spirit of the workshop, I wanted to kind of do a quick summary of what our infrastructure looks like from the instrument to the first storage. So what we have here on the left is one of the LIGO detectors, a very simplified version of, you know, Michelson interferometer, of which LIGO is a much more complicated example. And for those that I maybe should have given a little bit of more background on LIGO, I'm kind of assuming people know about LIGO. We have 2 facilities, one in Washington State and one in Louisiana. They're nominally identical detectors, observatories. And so the infrastructure that I'm going to describe here applies to both. But just for the LIGO project, we also have other worldwide partners whose detection principle is similar to ours, and I'll talk about our interaction with them in a minute. So sort of right at the instrument, we have you know, our digitization system that is handled in what we call these I/O chassis, where we have ADCs and DACs that interface with the sensors and actuators that are attached to the instruments. These I/O chassis are connected through an extended PCI bus to our front-end computers, which handle all of our real-time processing of the data, and you know, basically taking in all of those digitized sensor signals, doing processing of them, and sending those process signals back to the digital to analog converters to actuate on the instrument. Another thing I probably should have mentioned is that LIGO involves, you know, the LIGO detectors are highly controlled instruments. They're not passive. They're kind of unstable in some sense, and they need to be actively controlled. So one of the biggest technical challenges of LIGO is maintaining these hundreds or even thousands of digital control systems. And so all of this infrastructure I'm describing is the main guts of the real-time processing that enables all of this, you know, feedback control mechanisms that we use to control the instruments. These front-end computers are all kind of connected together via a shared message passing system over basically a shared memory system that goes over the PCI, the PCIe network. We use this currently we're using this proprietary system from this company called Delphonics. It's an interconnect. It's a very fast shared memory between computers. I'm not going to get into detail about how we do our real-time control. There's a lot of really interesting stuff in there, and I'm happy to answer questions about it offline if people have questions. We've kind of developed our own extension to the Linux kernel that enables us to do real-time processing. It's a very interesting system. And then I'll also note that we do all of our supervisory control through epics. So that's all of our GUI interfaces to the control system. Our automation is all done through epics, that sort of thing. All right, then we move into the data acquisition and the actual literal first storage, where the data that we wish to acquire from all of this real-time processing is kind of fed into a single entity known as our data concentrator that takes all of these data streams and bundles them together into a package that is then passed to another computer called a frame writer that writes all of that data to disk. That's our literal first storage there. That data that's packaged in these what we call frame files is passed to our analysis clusters for bulk offline analysis. And that's what we've been doing since the initial LIGO, since the conception of the project. But as the project evolved and we kind of got more sophisticated and realized that, it would be beneficial for us to analyze the data as we were taking it and try to lower the latency for reasons that I'll talk about in a minute, we kind of developed a low latency data distribution and stream processing system that was kind of an ad hoc add-on to our original sort of data processing pipeline. And that system also is what distributes data to to the control room where the scientists sit and engage directly with the machine, but also to scientists external to the laboratories who wish to analyze the data, and also to some analysis processes in the computer clusters. But this is the part that I want to actually focus on in this talk. And so, like I said, it's a little bit downstream of this initial data storage, but or in some sense actually parallel to it, because the data concentrator, where all the data from all of our sensors in all of our sort of pick-off points internal to our control loops, is passed directly into this low latency data distribution and stream processing system. And that's the thing that we're refreshing now. All right. So why do we have this sort of relatively new focus on low latency data processing? It's not actually that new, but it, in some sense, was an afterthought from initial LIGO. Certainly not for advanced LIGO. But the first low latency searches were deployed in LIGO in 2009. So before we made our initial detection, in our 6th science run. And that was where we first had our kind of very ad hoc attempts to take our offline searches for gravitational waves and make them work faster to try to produce event candidates, within, minutes or hours relative to months later. But this whole effort really came to fruition during advanced LIGO, which started taking data in 2015. Of course, as everybody knows, we almost immediately saw our first gravitational wave event, which was later confirmed to be our first discovery of gravitational waves. But almost just as exciting as that first discovery was a discovery in 2017 of a binary neutron star. So that first discovery was a binary black hole, which doesn't, that we know of, produce electromagnetic counterparts. But binary neutron stars we know to be the source of gamma ray bursts and huge optical explosions, electromagnetic explosions. And so when we detected our first binary neutron star event in 2017, we were lucky enough to have both LIGO detectors and the Virgo detector operating at that time. And we were able to localize the event in the sky well enough for optical telescopes to follow up on it and actually identify the optical counterpart to that event, which led to just a totally groundbreaking multi-messenger observation of what turned out to be this kilonova event. And it was a huge deal. These diagrams on the right are from the publication about the multi-messenger observation of this event. It's an incredible paper. I absolutely encourage people to read it. It's, I wasn't involved in the writing of it directly, but it really is one of the better scientific discovery papers I've read. And you can see in this kind of busy diagram, this is the time scale of the observations after the initial gravitational wave observation. That image in the upper left is the trace of the event sweeping through frequency space in the LIGO detectors. And then you have, GRB observations after that, optical observations. Basically, every telescope and observatory on the planet did an optical or a observation of this event in the aftermath. Obviously, a really big deal. Not necessarily because of this, but this really re-emphasized that we can help transient astronomy in a really impactful way by getting, informing in as low latency as possible the astronomical community about our observations and where in the sky we think they're coming from. So, getting these high quality alerts out to the astronomical community is not easy. It requires a lot of good coordination between all of the observatories in the network, particularly because getting good localization that would enable optical follow-up observations in a timely manner requires more detectors. I mean, you can't do it with one, you can't really do it with two, unless you have really good signal to noise ratio, which we don't have right now. We demonstrated that we can do it with three. 4 or 5 is even better. We can get those, localization area down really small when we have more detectors, which can allow for faster, follow-up observation. But also the latency is a major factor. There's a direct correlation between the speed with which we can issue these alerts and the quality of the science. In fact, one of our major efforts right now is to do early warning alerts so that we can potentially identify events and localize them before the merger actually happens. And so, in some sense, the holy grail for us is to be able to point telescopes at locations where an explosion will occur in the future, so that they could observe the initial explosion, the initial electromagnetic explosion of the event, which would just be incredible to see something like that. And then each observatory must also do a lot of work to kind of calibrate, clean up, annotate the data before distributing it into the searches, before distributing it, pushing it into the network of data streams that the searches are using to search for events. So this is a very schematic overview of the sort of domain that I'm talking about here. We've got, again, the instrument on the left, the what we call the raw data acquisition that feeds into this stream processing pipeline that culminates with these alerts being sent out to the astronomical community on the right. And in the middle of that, there's a lot of stuff. In particular, in that green box that says search, there's a whole bunch of stuff there that's happening there that I'm not going to talk about directly here, because that involves the streams from all the instruments and a lot of processing resources devoted to that. But I'm kind of focusing on this interstitial part here where each individual observatory has to do a bunch of stream processing on the data to calibrate, noise subtract, data quality, all of this kind of stuff that needs to be done as fast as possible so that we can get the data to the searches so that they have high quality data to work with to identify these event candidates. I'll note from the LIGO detectors, our raw data stream consists of, tens of thousands of what we call fast channels that are sampled in the kilohertz range, hundreds of thousands of slow channels, which are at 16 hertz. And then the block size that we're dealing with based on how our data acquisition system works right now is on 16th of a second blocks. So that's kind of our limiting factor of how fast we can move the data through the system, given how it is currently. And then overall, we're processing about 75 megabytes per second from each observatory. And that number kind of keeps creeping up as we keep improving the detectors. That's probably going to go up to above 80 megabytes per second in our next science observing run, which will start in 2027. But okay, so what are we doing to try to improve on this stream processing infrastructure? We have a bunch of goals that are basically come from us trying to, basically our lessons learned over the last decade of trying to do this, and the sort of inadequacies of our kind of ad hoc system that we put together, and just a laundry list of things that we would like to do better to make it to better enable the science. So one is this focus on stream processing as this is one of our primary science goals. It was not really understood in the community how important that was going to be initially. Like I said, it was kind of a little bit of an afterthought, but now we know this is really important. So let's really focus on it and do it right. We want to lower the latency of the data delivery. We want to modernize everything, use industry standards and tools and protocols. We want to try to unify our data access methods. Again, that's a function of it kind of being ad hoc, and we ended up with a bunch of data access methods that kind of created a little bit of friction for doing things. This is a really important part for the stream processing, is that we really want to enable, applications that can take the data streams and produce new data streams that get fed back into the system. That's almost in a sense literally what the stream processing is. So that needs to be very well robust and well handled. And this thing that I'm highlighting here, because I'll get back to it in a minute, is the auto discovery of data that is being published into these systems, both the raw and the derived data streams. And then we want to lower the barrier to entry. Our current system is kind of esoteric and is very difficult to develop in. And we want to make it much easier to develop applications in this stream processing space, because we believe that if we can do that and we can get more development in this space, we'll, enable that more people to be involved, better science. Okay, so what's the new architecture that we've been developing? It's based on the Aeroflight network protocol, which is HTTP gRPC based network protocol, very well established protocol for streaming the data, both in terms of the live streams of the data and offline streams. We're using Kafka for the derived data publication back into the system, which again is a very well-established industry standard network message passing system. And then in a subsequent phase, we're going to try to use Kafka to distribute data more broadly to the search pipelines, which we think we can do kind of more robustly and with lower latency than how we're currently doing it. And this project is well underway. We've been working on it for a couple of years now. We've got prototype services deployed at the LIGO sites, consuming all the raw channels. We have reference client libraries in Python and Rust. And we're focusing on this derived channel publication now as this critical part of the stream processing. Here's another kind of schematic overview of what this service infrastructure looks like. So the domain on the left, which I've enabled CDS, that kind of covers all the stuff that I talked about in the first couple of slides about that are control and initial data acquisition architecture. LDAS in the middle is the domain where we have our computer clusters that do this initial processing at the observatories, and the centralized clusters where we do our actual where we run our search pipelines. And then external, of course, is external applications that are run on people's laptops or at other facilities. And so the data streams into a Kafka pool where basically everything is gathered together. Then on the right, we have this sort of, in some sense, you might call it a secondary data storage that collects all the data that's being published into these Kafka pools, publishes it into a synchronizing time series database where it's also then archived in offline storage. And then we have these Aeroflight servers that sit in front of these, the Kafka pool and the synchronizing time series database to serve the data out to all the client applications. And then in orange, you see these stream processor applications that would stream the data from the flight servers, do some processing on them, and produce these derived channels that get published right back into these Kafka publication pools for essentially instantaneous access by other client applications. Okay, so that's all going pretty well. Sort of in the background for this development, the gravitational wave detector field is undergoing kind of a big seismic shift right now in how we're organizing this worldwide network of ground-based detectors. We've up until this point had this network of sort of distributed collaborations. There's a LIGO scientific collaboration, Virgo collaboration, the Kagra collaboration, and we're embarking on a effort to try to unify all of these disparate collaborations that have been still working well together into a single worldwide international gravitational wave scientific collaboration that's sort of at the moment called IGWIN. So there's a lot of effort happening on that front. So how do we think that this Arrakis system can help improve the coordination between these facilities, strengthen this international network, and better enable this, stream processing so we can get more better transient events. So there's this data mesh concept that is been floating around in industry and the tech world for a while that is actually very relevant to what we're doing. I won't go into it in too much detail, but it essentially is about how to think about federating data services across different domains to enable a kind of cohesive access to these to data. I'll let people look over this, but the point is that it's a kind of way to think about federating data sources. And so we're thinking about this concept, the whole time that we've been developing this Arrakis infrastructure, and kind of because of one of our fundamental desires to do this kind of auto discovery, it actually kind of enables this data mesh concept kind of inherently. And so one of the things that what we've built is, by using this Aeroflight protocol really helps enable this. So as in this diagram on the right, you can see that this is already kind of enabled by the infrastructure we have right now, that a client can request streams from sources. It doesn't have to know anything about the provenance of the sources. And the service infrastructure will provide all that the client needs to know to stream the data from wherever it is living. And so, the client will talk to an initial service, which will then be talking to some sort of a distributed domain registry of all of the sources that are available, and then provide that information back to the client. And then the client kind of transparently on the background will in parallel get the streams from all the available sources and deliver them to the application. And then, the other part of enabling this data mesh is, the common shared protocols, APIs, standardized data types, stuff like that. And, that's kind of all a process of how we're trying to build this stuff out right now. And so we're really hoping that this project will, eventually grow into something that will be an important part of this new IGWIN worldwide network, to really help enable the scientists to easily get all the data that they're looking for from all the facilities, and so that we can help do the most quality science that we can. I will note that one thing that we've been struggling with a lot recently is this sort of distributed registry of the domains and the sources of the data is one of our bigger challenges right now, that we're sort of trying to think a lot about how that that infrastructure can be put together. But I think we'll be able to do it. And the technical aspects of the services for streaming the data, I think we've got are well in hand at the moment. And we're going to try to do some prototype searches with this new infrastructure before the 4th observing run of the network is over later this year. And then we'll have a couple of years to really get this stuff production ready for our 5th observing run, which should start, I believe, in 2027, or that's where it's scheduled to start at the moment. So anyway, that's it. Thank you guys for listening, and happy to take any questions.